Hello. Today we're going to talk about finding second-order partial derivatives. This is problem number 49 on page 819 of, what is the book name? Thomas's Calculus 13th edition, Early Transcendentals. Okay, so we're talking about second-order partial derivatives. So in our last video we talked about finding first-order partial derivatives. Now we're talking about second. So if we're thinking about a single variable function first, we can look at something like f of x. If we're finding the second order derivative, or the second derivative, it's just going to be f double prime of x. So if we're looking at in different notation, this is going to be df dx. This one, the second derivative, is going to be d squared f over dx squared. And that comes from, I'll just draw a little thing here. This is the same exact thing as this. It's going to be d dx of df dx. And then let's put that, that's an x. So this is df dx, this is saying the derivative, this is our first derivative, and this is the differential operator. It's saying take the derivative of the first derivative, which is how we get to the second derivative. That's basically what that's all saying. So if we're looking at second order partial derivatives, this is not partial, these are just whole derivatives, these are normal derivatives for single variable functions. Partial derivatives, multivariable functions. So we're going to look at that over on this side. So second order partial derivatives. If we have, let's say, a function of x and y, we have two first order derivatives, df dx and df dy. Now what we can do to each one is we can apply the differential operator to each one, except in when you have a multivariable function, in this case of two variables, you're going to have two different differential operators. We're going to have d dx, but you're also going to have d dy, because they're both variables. So if we do that to each one, we can do d dx to df dx. We can do d dy to df dy, but we also can do d dx to df dy. And in another video, we're going to show that this is the exact same thing as a d dy of df dx. Now, writing what those equals, this is simply going to be d squared f over dx squared. There's an x there. This is going to be d squared f over dy squared. And this is called a mixed derivative. That's going to be d squared f over dx dy. Or if you write it in a different order, d squared f over dy dx. And these are all the same things, these are the same things, and these are the same things. So this is just showing the progression. So I'm going to clean this up a bit by erasing some of that stuff. But that's just to show you where those second derivatives came from. So I'm going to erase this over here. And I'm going to erase this over here. So I'm going to write out again what these second order partial derivatives that we're looking for are. So let me get my pen tool. So what we're finding essentially, d squared f over dx squared, d squared f over dy squared, and then it doesn't matter what the order you write in the bottom, I'm just going to put x first, so dx dy. Okay, so that's what we're finding. So let's start off with d squared f over dx squared. And what I'm going to do, I'm just going to zoom in a little bit so we get more space. All right. So I'm going to do that one in red. So we're looking at d squared f over dx squared. Like we just said, that's d dx of df dx. Now in this case, f we can just call w. So f of xy, we can say that's equal to w, because w is a function of x and y, so it's the exact same thing. We could change this to a w if we wanted to. It doesn't matter. It's going to be the same calculation. Okay, so let's do that. So first we have to find df dx. Let's make that our first priority. So we can just keep that out here. So dx. All right. So this right here is going to be a product rule because we're doing it with respect to x, and you have an x here and an x. That's going to be like inside parentheses. So derivative of the first is going to be 1 times the second, which is going to be sine of x squared y. And then we're going to add the first, which is x. Now we're going to take the derivative of the second with respect to x. So the derivative of the inside, this is just like what we did last time. It's like a product rule. Remember, we said that multivariable functions have they follow the same differentiation rules as single variable functions. So the derivative of the inside, like we normally do for a chain rule, derivative of the inside with respect to x is going to be 2xy times the derivative of the outside. So the derivative of sine is just going to be cosine. And we're going to do that evaluated at the inside. So x squared y. And why I wrote the parentheses there, but not up here, I have no idea. Oh, right there. Okay, so we're going to simplify this down. So we're taking dx of sine x squared y plus 2x squared y cosine x squared y. Okay. So I'm going to continue that over here just so we have more room to write. All right. So now we have to differentiate this whole piece of junk right there with respect to x. Okay, so let's first start off with sine of x squared y. That's exactly what we just did up here, and it's this part right here. So, except for that x. So what we're going to do, derivative of the inside, that's going to be 2xy times the derivative of the outside, which is the derivative of sine, which is cosine, evaluated at the inside, which is x squared y. Okay, so that's the derivative with respect to x of this. Now we're going to do the derivative of this with respect to x. Again, that's going to be a product rule. So the derivative of 2x squared y with respect to x, so we're going to add that. The derivative of that with respect to x is going to be 4xy, because we bring that 2 down, we subtract 1, so we just get 4x, and then y is considered constant, so we put that y there. Okay, so that's the derivative of the first times the second, which is going to be the cosine of x squared y, plus the first, which is just going to be that 2x squared y, times the derivative of the second. So we're going to do it just like we did with that sine of x squared y, just it's going to be cosine this time. So the derivative of the inside is going to be 2xy times the derivative of the outside. So the derivative of cosine is going to be negative sine, and we're going to evaluate that at the inside, x squared y. Okay, so let's clean this up a bit. So we're going to say that equals, we have this 2xy cosine of x squared y plus 4xy cosine x squared y. And then we're going to have this minus out here, so it's going to be minus, then we have 4 because that's 2 times 2. Then we have the x times the x squared, which is going to be x cubed. Then we have y squared sine of x squared y. Now, all in all, you're going to get, these are the same exact thing, just we have the 2 and the 4 here. Well, switch. So we're going to have 6xy cosine x squared y minus 4x cubed y squared sine of x squared y. So that's our second derivative with respect to x. Now, let's do it with respect to y. So, let's see, we can use this with green. So, that's going to be d dy of df dy. Now, we don't know df dy, so we're going to find it. So this is going to be d dy. Okay. Let me move this. Oops. So we can just see our function there. Okay. So we're taking the derivative of this with respect to y. So we can notice that this x is just going to act like a constant out there, so we don't necessarily have to worry about that. So now we have to take the derivative of just sine of x squared y with respect to y. Okay, so we have this constant out here, so we're going to put that x. All right, so now we're going to do it just like we did with respect to x, where we had, this whole piece right here, except we're going to do with respect to y. So the derivative of the inside with respect to y, that's just going to be x squared. Now the derivative of the outside, which is sine, the derivative of sine is going to be cosine, and now we're going to evaluate that at the inside. That's x squared y. So that's going to be d dy of x cubed cosine of x squared y. Okay, that's a lot simpler than before. It's mainly because we don't have a product rule here, because this is just acting as a constant. That's mainly why. Okay, so now we're going to find this piece here. We're going to take the derivative of x cubed cosine of x squared y with respect to y. So let's do that. Okay, so remember, this x cubed is just going to act like a constant there, so we can just put that out front and don't have to worry about that. Okay, so now we're going to take the derivative of cosine of x squared y. Again, that's kind of like a chain rule there. So the derivative of the inside with respect to y is just going to be x squared. Now we do the derivative of the outside. So the derivative of cosine is going to be negative sine. And we're going to evaluate that at the inside. And what that comes out to is that's going to be negative x to the fifth sine of x squared y. Okay, so this is our d squared f over dy squared. I'm just going to square that so you guys know what it is. Oops, sorry about that. That is our d squared f over dx squared. So now what we have to do is just find the mixed derivative. Okay. I'm going to change back to that, and I'm going to do this in orange. So our mixed derivative, dx dy. So what this is going to be d dx of df dy. Now we could do d dy of df dx. In this case, it's actually easier to do it this way that I wrote, because df dy is a lot simpler. Okay, so let's write that. So we found df dy in the previous one, and that's going to be our x cubed cosine of x squared y. So x cubed cosine of x squared y. Okay, this is a lot like the first problem. In the first problem, oops, undo that. In the first problem, you saw we had to do the product rule because we were taking the derivative of this with respect to x. In this case, it looks a lot the same, really. It's going to be the same fundamentals. It's a different setup to the problem. Okay, so let's do that out. So this is a product rule. The derivative of the first is going to be 3x squared times the second plus the first, and now we're going to do the derivative times the derivative of the second. So it's just like we did in the past problem. So the derivative of the inside is with respect to x, except the last problem we did with respect to y, so it's a little bit different. So with respect to x, this is going to be 2xy. The derivative of the outside is going to be negative sine, and then we're going to evaluate that at the inside. That's x squared y. Okay, so I'm going to move over here and just write that out. Okay, so we have 3x squared cosine of x squared y, and that's going to be a minus. We have 2x to the fourth y sine of x squared y. And that's about all we can simplify that down. So That's our mixed derivative. So we found all three second-order derivatives. So to recap what we did here. It said find all second-order partial derivatives. We noticed that there are multiple forms. If we just had one variable, it would be d squared f over dx squared. If it was a function of y, it would be d squared f over dy squared. However, this is a partial derivative, so we have these little partial signs. That's indicating that's partial, but we also have a mixed derivative right here. So when we found these, we realized that we had this notation kind of hidden in that form. So we could take the derivative with respect to x of df dx, or the derivative with respect to y of df dy. We could even extend that to taking the derivative with respect to x of df dy, or you could do d dy of df dx. Either way, that would come out to the same. So we went through these processes, noting that we could do the same rules of differentiation with multivariable functions as we did with single variable functions, in this case being the product rule and the chain rule with trig functions. And we also have to note that when we take the derivative with respect to one variable, all other variables are considered constants. And I hope that helped. See you next time.